Question 10. Write down the modulus and argument of the complex number w, where w is equal to 1 plus I root 3. So again, this is where knowing our 1, 2, root 3 triangles come in, because this is a 1 and a root 3, so we kind of know where this triangle is going. So let's do a quick sketch of it. Here's my Argand diagram. I'm only going to need the first quadrant because that's where this vector will lie. You go out 1, up square root 3. So I haven't really made those two look very different. So you end up with something that looks like this. Really haven't made them very different at all, sorry. Where this is 1, 2, square root 3. This is the bigger angle, so this is going to be 60 degrees. It's pi upon 3. This one will be 30 degrees, which is pi upon 6. So again, just by knowing this triangle straight away, I can write down that modulus w is equal to 2, and that the argument of w is equal to pi upon 3. So hence find the set of values of w, the set of values of the positive integer n, for which w to the power of n is real, and show that for these values of n, the value of w to the n is either 2 to the n or minus 2 to the n. So if you look at this, right, you look at an Argand diagram. This is a terrible Argand diagram, by the way, so don't look too closely. But you get the idea. If this is our Argand diagram, where are the real numbers on this Argand diagram? Well, the real numbers are along here, right? They're along the real axis, funnily enough. And what do you notice about all of these real numbers? The argument is either 0 degrees, or 0 radians, if you will, or the argument is pi radians. So what is this question actually asking us? It's asking us for the values of the positive integer n, for which the argument, what we want to find is where is the argument of w to the power of n equal to 0 or pi. And of course, we know that the argument doesn't have to be exactly equal to 0, it just has to be equal to 0 or 2 pi or 4 pi or 6 pi. So like some multiple of 2 pi, and this has to be some multiple of pi plus 2 pi. So pi, 3 pi, 5 pi. So what do we notice? We notice that we want to find the argument of w to the n is equal to k times pi for some integer k. Doesn't even have to be positive, it can be negative integers as well. So when does this happen? Well, let's check it out. Argument of w to the power of n. Well, we know that's going to be n times the argument of w, right? So this is going to be n times pi upon 3, and we want this to equal to k times pi for some k that is an integer. So what does that mean? What values of n will this happen for? Again, we can just cancel out some things here, but you see that this happens when n is equal to 3k. And what does that mean? If n is equal to 3k for some integer, well, that means that n is a multiple of 3. So, yeah. So what is it? So this is n equals to 0, obviously, 3, 6, 9, and so on and so forth, right? And what does that mean? Well, are we asked to find the set? Yeah, we're asked to find the set. So the set is the set of n element of z, such that such that there exists some k in z where n is equal to 3k. So, or if you want to put it another way, it's a set of n integers n such that n is a multiple of 3. So we look at this and we ask ourselves, well, holy holds, how do we know that it's going to be either 2 to the n or minus 2 to the n? So this is kind of like the second part of this question. So if I have n is equal to 3 to the k, what is w to the power of n? Well, that's going to be, if you recall, let's just write this in exponential form. This will be 2e to the I pi upon 3 to the power of n, right? So this is 2 to the n and this is e to the I pi over 3 times n. But we already know that that is just 2 to the n e to the I pi over 3 times 3k, right? And so this is just 2 to the n e to the I k pi. And so what's that equal to? Well, that is equal to 2 to the n if k is even, and is equal to minus 2 to the n if k is odd. Because if it's even, then you've got a repeating value of 2 pi, so the actual argument is 0. So e to the I 0 is just 1, okay? And if it is odd, then you've got either pi, 3 pi, 5 pi, which comes back to be pi, and e to the I pi is just minus 1. So you get 2 to the n times minus 1 minus 2 to the n if k is odd. So we've shown what we're asked to show, that it's either 2 to the n or n, and we've given conditions if k is even or if k is odd. So the last part, express w to the 100 minus w conjugate to the power of 100 in the form ki, where k is real, given the exact value of k in non-trigonometrical form. So what do we do? Well, w to the power of 100 minus w conjugate to the power of 100, that's actually equal to w to the 100 minus w to the 100 conjugate. That the order doesn't matter here. And so if you look at this, what does this say? This is just equal to 2i times the imaginary part of w to the power of 100. So now all we have to do is find out, well, what is the imaginary part of w to the power of 100, right? So what is that going to be? Well, it's 2i, and then we get what the imaginary part of, and recall w is root 2 e to the I pi upon 3 to the power of 100. Actually, sorry, there's no need to do that. I'm being a bit silly. Because I know what the imaginary part of w to the power of 100 is going to be, right? Because I know the real part is 0. So I'm just going to write in trigonometric polar form, where this would be 2 to the power of 100, right? Then 0, which is the real part, plus I sine, and that would be 100 times pi upon 3, right? But fortunately, I can tell you what 100 pi upon 3 is fairly easily, and you can work that out yourself, and you can check it on your calculator even. So this is 2 to the 100 plus I have forgotten one little thing, and I should have written imaginary part in here both times as well. So this would be 2 to the 100 I times I, and then sine 100 pi over 3. All that is minus root 3 upon 2. So what do I get? I would get... No, sorry, I don't need the imaginary part there. That's fine, because, sorry, I was forgetting. The imaginary part, I know I can just write a 0 there, right? So what do I get? This is just 2i times 2 to the 100 times minus root 3 over 2. This is just minus root 3 2 to the power of 100 times I. So therefore k is equal to 2 to the power of 100 minus root 3 times minus root 3. And we're done.